at this thing. It's fucking sick. It's got a capstan drive, rolling contact joints, compliant mechanisms, tendon drive. But before I get too deep into this, I want to talk about these. This is an awesome little board that Will and I have been developing for the RoboDog project. It's got a ton of features that I think is going to make it awesome for you guys doing your own projects. Starting on the bottom, it's got a ESP32C3, which has built-in Wi-Fi and Bluetooth on board, a 5-volt regulator which is used to power the ESP from the input power, which can be anywhere from 12 to 24 volts, and our awesome sponsor who has helped us so much on this project. They deserve the biggest shout out and their name right there on the board. PCBWay, thank you again. On the top of this board I have a XT30 power input which can actually be replaced by a USB-C PD 20 volt port on the bottom of the board. This power input is used by the H-bridge motor driver and the H-bridge output to power our DC motors which we use on the RoboDog. The H-bridge driver can output 7 amps continuously or 10 amps peak, and it can be used to power motors, solenoids, high power LEDs, or anything else that you want 12, 24 volt, 7 amp, full PWM forward or reverse voltage on. Next we have the CAN ports. We have 2 CAN so that you can do input and output CAN bus, and these are used to daisy chain all the boards together for communication and power. These handle 5 volt so that you only need a single 5 volt regulator to power your entire daisy chain or stack of boards. We also have a 120 ohm CAN bus terminating resistor on the board already with a very easy to solder jumper to activate it. This means that you don't have to add your own terminating resistor. Next is a 5 volt level shifted I2C port. The reason we decided to make this level shifted is for compatibility for all the major name brand I2C device manufacturers like Adafruit, Seed Studio, and SparkFun. Through this port you can run small displays, and you can also use other devices or anything that uses I2C. I personally use it for a AS5600 magnetic encoder to read the angle of the RoboDog's joints. Up next is a 3 volt GPIO port, and the cool thing about this port is that you can actually use it for I2C as well. This port has 2 GPIO ports, power and ground. To the right of that is actually a 6-axis IMU built right into the board. You can communicate to this 6-axis IMU through the same I2C lines as mentioned previously. Just above that I have a 4-pin dip switch, and this is actually used for setting the CAN address externally. This means that you can upload the same code to up to 16 boards and set each of their addresses right here from this dip switch. And to the right of that I have a single GPIO header added on just for expandability. You can solder up a standard set of pins to this and use it for a servo or whatever else you might want standard GPIO control of. A cool thing about this board is that they're actually stackable, so you can take 2 of them, stack them just like this, and run CAN bus that easy, and now you've got shared power between 2 boards and communication going from one to the next with 2 open CAN bus ports so that you can keep adding to your daisy chain. All documentation for this board is open source on my website, so you can go there, download the KiCad files for it, and upload them directly to your favorite PCB manufacturer like PCBWay. They make it about as easy as it could possibly be to order them. Additionally, I'm going to have a small number of these boards in a full kit, including the heat sinks, ESP32s, 5 volt regulators, and any other small components that you might need on there on my website for sale. We're also working on expanding these boards to include other models for different tasks. The next one up is going to be a dedicated comms and GPIO board where it's essentially cut off right here so that there's no motor driver circuitry, Instead, you'll have added GPIO pins, but you'll keep the CAN bus, I2C, and other features on this board. That board will be great to use as the master for controlling all of the puppets in the Robo Dog. We're also working on a dedicated servo controller board, a stepper controller board, and in the future hopefully a BLDC motor controller board. If you want to learn more about these, check out my post on my website. I go into much greater detail, and we have a data sheet uploaded as well. I really hope you guys like these. I think they're awesome, and I can't wait to see them used in more projects. I'm back. Time to talk about the legs some more. Each joint has its own magnetic encoder for reading the current angle of the joint. I have this on the joint directly as opposed to on the motor so that I can have the tightest closed loop feedback possible. This guy speaks over I2C to the master. The master for the knee is actually mounted right here on the hip. The hip motor controller is actually mounted on the back right here, along with the master, which communicates to all three motor controller boards for this leg. And the master for the ankle is mounted, a little hard to see, on the back side of the ankle, if I can get it to focus. There you go. Each one of these joints runs a closed loop PID targeting function. It receives the target angle over CAN bus from the master, which you saw mounted on the back of the hip. The master receives all three target angles over a serial connection from my laptop, which you can see right here. I have a Python GUI which I use to control the target angle of each joint. From here I can use these sliders to actually move the knee around, or the hip. I also have a record and playback function which comes in handy. So I can go there. And I can control the speed of playback. Let's turn it up to 4x. Ooh, she's angry. And I can turn all three motors off because they are quite annoying sounding. So a cool thing that I can do with the record and playback function is that I can hit record and I can actually input some rough walking movement. I can stop recording, I can hit playback, and you can see that the playback is pretty rough. It's not clean. Right now, the data that I record is the angle position of each motor as I move the leg around, and then it's played back at 1 to 10x speed. I found that the input that I give the robo leg is quite shaky because there's a lot of stiction, and so you're kind of fighting it as you're moving this leg around. And so I implemented a smoothing function, which I'll name here, and that helped a lot, but it's still shaky. What I really need is a proper amount of coding for the path of the foot. I need to map out the position of the foot all over a XY coordinate grid, and then I need to plan out the actual path that the foot takes on a real dog, and then I need to hand program that so that it's not just this ugly synthetic movement, because it's just not working like that. It's pretty ugly. I will say though, I'm incredibly happy with how this project is turning out. This thing is so much faster and stronger than I was expecting. I was actually able to pick up this which is a 18.5 pound weight with this leg. I tried getting a force reading out of a bathroom scale, but the scale kept turning off and the foot kept slipping off of it. I did get a short reading of 1 stone, 2 pounds, which is something like 16 pounds total.
Oh, we just hit 11.
We did hit 11 previously.
All of the pieces starting to
Yeah, but it wasn't a accurate reading. And I know that this foot can put out some serious force. In fact, I'll show you right now. It's strong. It could lift some weight. I don't really know how much. I'm not being scientific about it. I've done no math. But I'm happy with it. Along with programming a proper walking gait for the movement of the leg, I also need to spend a lot more time working on the code for the motor drivers, because right now they are solely PID for the target angle, but I also have current feedback, which should give me a rough idea of torque output of each joint, and I want to integrate that along with a speed limiting portion of code so that I can more accurately give target position, force, and rate at which I reach the target. That also means that I'm going to have to update the code for the master and the code for the GUI, because both of those are now going to need input and output for force and maximum speed or target speed. And all of this coding takes quite a bit of time. I'm not a comp sci major, so coding is not really my forte. Luckily, I've got some good friends who are helping me out, but it's still by far the most difficult part of this project for me. From here, I don't really know where I want to go. I've got enough motors to make one more leg. It takes about 4 hours to assemble a whole leg, and I've had to disassemble and reassemble this leg probably 4 times now, which really sucks. I could go ahead and order all the parts to build out a whole dog. I don't think I'm ready for that yet. I think I would like to do a whole lot more coding and testing before I get there. But I'm kind of interested in making some sort of fucked up ostrich cart walking thing that drags behind a little cart. I think that would be fun, but I'm also willing to hear your guys' recommendations and see where you want this project to go. Anyways, that's it for this video. Let me know where you want this project to go. Just ignore that. Don't worry about that. That's fine.
What the fuck is ST?
I have no...
23 pounds.
Yo! So we were putting out 23 something, or...
Because you're at 1.8 ST?
I was at 1.2. So it might have been like 15.
Damn.
That's pretty good. That's actually really good. Wow, that makes me feel so much better than the dumbass 1.2 pound.
Also, you were effectively losing force on your vector.